Today's notes are on right triangle trigonometry. This is section 4-3 in your textbook. And the first thing I've written there is SOHCAHTOA. Now I tell you what, if you know SOHCAHTOA, you can do a majority of all trigonometry problems that you'll ever see. So I just want to start with a right triangle over here. So I'm going to draw a right triangle. Let's put theta right here in this lower left-hand corner. And I'm going to give it some dimensions. Let's call this 8. Let's call this down here 15. Let's call this 17. Okay, now SOHCAHTOA tells us that to find the sine of any angle, we take the opposite side over the hypotenuse. Cosine of any angle is adjacent over hypotenuse. And tangent of any angle is opposite over adjacent. Now we do have some reciprocal trig identities down here. So if you know the first three of these, if you know SOHCAHTOA, you can come up with the second three. So cotangent of any angle, in this case would be 15 over 8. Secant would be 17 over 15. And cosecant would be 17 over 8. Okay, so no SOHCAHTOA. Don't be afraid to draw a diagram. Let's jump into another example using that. So first example, well, let's use this special right triangle to find sine, cosine, tangent, cotangent, secant, and cosecant of this 45-degree angle. Well, it is a special right triangle, which we saw before, so that means we can give it these certain dimensions. Well, I gave it the wrong dimension. Let me get rid of that. So in your geometry days, you learned that if this is an isosceles right triangle, these two legs have the same dimension. The hypotenuse is square root of 2 times that dimension. Okay, so there's our dimensions of this special right triangle. Sine of that 45-degree angle is opposite over hypotenuse, and you might say, hey, wait a minute. Having that over 1 is convenient here because opposite over hypotenuse, if the hypotenuse is 1, we don't need to include it in there at all. We could write over 1, but we don't have to. So sine is really just this dimension over here, if the hypotenuse is 1. Cosine is adjacent over hypotenuse, and we see the same thing happening. Now tangent, let's think about this. Tangent is opposite over adjacent. Before you write that all out, just realize that, hey, those two quantities are the same. So if you put one over the other, you'll get a value of 1. Okay, let's use the reciprocals. So cotangent is 1 again. Secant is the reciprocal of cosine, so that's going to be 2 over the square root of 2. Which is the right answer, but if we rationalize that denominator, we'll get 2 square root of 2 over 2. We'll get just the square root of 2. And likewise, cosecant, since it's the reciprocal of the same quantity, will also get the square root of 2. Okay, let's do the same thing with our other special right triangles. So I'm going to label the sides of this special right triangle, thinking back to our geometry days. So we've got 1/2 1 and square root of 3 over 2. Now the sine of 30 degrees from this 30-degree angle, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So we've got 1/2 over square root of 3 over 2. Since they're both over 2, we can just write that as 1 over square root of 3. And we can rationalize that denominator, right, it's square root of 3 over 3. Realize all these quantities are equal. It's just different ways of writing it. Okay, cotangent. So I need the reciprocal of tangent. I'm not going to use the reciprocal of this last quantity. I'm going to use the reciprocal of this one, which is much easier to work with. That's just the square root of 3. Secant would be 2 over square root of 3, which if we rationalize is 2 square root of 3 over 3. Cosecant is going to be 2 over 1. Okay, now we also have to find those same quantities for this 60-degree angle. We're going to get the same values, but just different quantities for different ratios because the triangle hasn't changed. So now our opposite becomes our adjacent and vice versa. So sine of 60 is going to be square root of 3 over 2. Cosine of 60 is 1/2. Tangent of 60 is square root of 3 over 2 over 1/2. That's just going to be square root of 3. Cotangent is the reciprocal of that, which is square root of 3 over 3. Secant is the reciprocal of cosine, and cosecant is the reciprocal of sine, which is 2 square root of 3 over 3. Now here's something that you should notice here. You should notice that the sine of 30 and the cosine of 60 are the same. And likewise, sine of 60, cosine of 30 are the same. You should also notice that the tangent and cotangents of these angles are the same, and that the secant and cosecant of these angles are the same. Now that's not just a coincidence, and that's not just something that happens with these special right triangles here. That's something that happens anytime we look at these two angles, and those angles add up to 90 degrees. So there are some different theorems or different properties that you can write down if you choose, but really all this is saying is, let's say theta is 10 degrees. The sine of an 80-degree angle is the same as the cosine of a 10-degree angle. Okay, just like the 30 and 60 on the previous page. So all these properties are really telling you is that if you have two angles of a right triangle, the sine of one is going to be equal to the cosine of the other. Okay, now that we've got that down, let's move on to another example. This one says if the sine of theta equals 3/8 and theta is in quadrant 1, we got to find each of these quantities. Best bet here, start with a diagram. There are ways to do this without a diagram, but they are too much work for us. But if we start with a diagram, we know that theta is in quadrant 1, so I'll put theta right here in this first quadrant. Here's a right triangle. The sine of this angle opposite over hypotenuse is 3/8. And before we go any further, we need to use the Pythagorean theorem to find this missing side. So a squared plus 3 squared equals 8 squared. If you continue with that, you get the square root of 55. Once your diagram is drawn, coming up with these answers is relatively easy. We know cosine is adjacent over hypotenuse. We know tangent is opposite over adjacent. Now just a note right here. I know in your geometry days your teacher told you that you always had to simplify this square root, this radical in the denominator. When you take calculus next year, your teacher will tell you that you don't have to do that. So why do we tell you you always have to in one course and then you don't have to in another? Don't ask me, it doesn't make sense. Guess what? This quantity is correct. But it is also correct to rationalize that denominator and write it this way. So just realize that sometimes it's easier to work with it like this on the left, sometimes easier like this on the right. Okay, now our next three answers are going to be reciprocals of what we have before. So let's come up with those. Cotangent, here's a case where this is easier to work with. Take the reciprocal of this, we get square root of 55 over 3. Secant is going to be 8 over square root of 55, which can also be written as 8 root 55 over 55. And cosecant is 8 over 3. Again, if you have the diagram, this problem is relatively easy. So let's do another one of these, and I'm going to jump right in with the diagram while you read the problem. It's saying this is some angle in quadrant 4. So I'm going to draw this right triangle. Now when we draw these, always put theta here by the origin, and always draw your vertical segment of your triangle so that it intersects with the x-axis. Sometimes I see students draw their right triangle so it goes over this way, make a right triangle. We don't want to do that, so I need to get rid of that stuff there. And we know cosine, which is adjacent over hypotenuse, is 12 over 13. Using the Pythagorean theorem, we get a quantity here of 5, which actually is incorrect because this goes downward. Since this goes down, this quantity here is negative 5. So keep in mind, any quantity that goes to the left or down is going to be negative. This value here, the hypotenuse, is always positive because it's a radius of a circle, okay? So that's always positive, but any quantity down or left would be negative. Okay, now that we've got this, now I think in my directions I forgot to ask about the sine of theta, so we'll start with that. So that's going to be negative 5/13. Cosine is 12/13, and tangent is negative 5/12. Now the reciprocals. Cotangent is going to be negative 12/5. Secant is going to be 13/12. And cosecant is negative 13/5. Okay, so if you can come up with your sketch, coming up with the answer is actually the easy part. All right, So speaking of easy, let's do some more easier examples. Let's use a calculator to find these quantities. Now, I'm not putting this example in here because I think you can't type these in your calculator. I'm putting these in here because I want to warn you about something. If you look in your calculator's upper left corner, there's a key that says mode. And if you press that key, you will notice that either the word radian is highlighted or the word degree is highlighted. So we have to be really, really careful throughout this unit when we're working with a calculator to find these quantities, because these first two have degree signs by them. So to find these on your calculator, you should have the word degree highlighted. This middle one is a radian measure. There's no degree sign. In fact, sometimes we could even write this. This is asking for sine of 10 radians. Until there's a degree sign, it is a radian quantity. So we have to be careful with that. So let's get rid of that there. Let's get out our calculators, press your mode key, make sure the word degree is highlighted. Once it is, you can type in your calculator the sine of 10, and it'll give you an answer of 0.1736 or so. Now to do the second one, we have to press the mode key, change that mode to radian mode, and then we can type in there the sine of pi, and pi is over on the right hand side of your calculator screen, divided by 5, and you'll get something like 0.5878 or so. Now this last one, cosecant. You can look at as hard as you want. You won't find a cosecant key on your calculator, but we know cosecant is the reciprocal of sine. So this is like 1 over the sine of 20 degrees. So first of all, check your mode. Make sure your mode is in degree mode because you have that degree sign. Then you can type in there 1 divided by the sine of 20 degrees. And it'll take care of that for you. It'll give you an answer of about 2.924 or so. Okay, so the key to these, make sure you're in the proper mode. All right, let's continue. This next idea, these are what are called trigonometric identities. Now, the first identity here, the tangent of theta equals sine of theta over cosine of theta. I just want to go back to one of these previous examples we had here. Let's talk about this one. Notice tangent was this quantity divided by this quantity. So tangent opposite over adjacent, it's always going to be sine divided by cosine. So going back to this idea, the reason this is the case is because tangent is opposite over adjacent. Sine deals with opposite, cosine deals with adjacent. Cotangent is the reciprocal of tangent. So take that fraction, flip it around. This next one, this is what's called the Pythagorean identity. This comes from the Pythagorean theorem. Pythagorean theorem says a squared plus b squared equals c squared in a right triangle. And when we're thinking about these right triangles with a quantity of 1 for the hypotenuse and sine and cosine for opposite and adjacent, we get this Pythagorean identity. And then from that identity, if we divide every quantity by sine squared, we get this next one. Divide every quantity by cosine squared, we get this next one. Now these identities, we're not going to use them a ton at this point, but they're going to come up a lot in our 5th chapter. Chapter 5, we're going to use these a lot. We're going to see them a little bit now. We're going to see them a lot later on. So at this point, it's nothing you have to completely understand, but if you're familiar with them, it'll help you out down the road. Okay, let's jump into some more examples. 6th example of the day, let's use special right triangles to solve for theta. So the hint in this problem is we're using special right triangles. So I'm going to draw up here a 45, 45, 90 triangle. I'm going to label some of the dimensions on this triangle. That'll help us out. And I'm also going to draw a 30, 60, 90 special right triangle and label some dimensions here as well. And let's see here. So there's 1, there's 1/2, here's square root of 3 over 2. All right, so these problems are a little different from what we've seen before. If you look at the first one, it says the tangent of theta equals 1. So that's like saying find the angle whose tangent equals 1. Well, if we're looking for an angle whose opposite over adjacent equals 1, that means opposite and adjacent must be the same. That means theta must be equal to 45 degrees. Now this one's saying find the angle whose opposite over adjacent equals square root of 3. So it won't be 45. In fact, it won't be 30, but look at this 60-degree angle. Opposite over adjacent. Those 2's are going to simplify, so it's going to be square root of 3 over 1. So the angle that works is 60 degrees. All right, this one. Find the angle whose cosine, whose adjacent, is square root of 2 over 2. That's 45 degrees. And this last one, find the angle whose cotangent is square root of 3 over 3. Now, I always have trouble with cotangent, so I'm going to write this as tangent. I'm going to write a reciprocal. And sometimes this quantity is easier to work with. Sometimes it's easier if we rationalize the denominator. So just realize that all of these quantities are the same. So the angle whose tangent is square root of 3 over 1, hey, that angle must be 60 degrees. So one big key on that is that we're talking just special right triangles. Another key is hey, just take a look at those diagrams we have. Find the angle whose sine, cosine, tangent, whatever it happens to be, equals those quantities. Okay, let's give ourselves a little geometry review. We need to solve this for x. So remember, to solve these problems, we're going to use SOHCAHTOA. We've got opposite, we've got adjacent. So that tells us the tangent of 40 degrees equals 10 over x. If we multiply both sides by x, and then divide by the tangent of 40, we get x equals 10 over the tangent of 40 degrees, which our calculator can handle, but make sure your calculator is in degree mode. If it is, you can type this in just as is, and you'll get x is going to be about 11.9 units. Now you could have done this another way. You could have said, well, let's talk about this 50-degree angle and said the tangent of 50 equals x over 10. Guess what? It works out the same way. All right, let's look at a similar example. So we're solving for x here. So from that 29-degree angle, we have adjacent and hypotenuse. So we can say the cosine of 29 degrees equals 24 over x. Multiplying both sides by x and dividing by cosine of 29 degrees, we get x equals 24 over the cosine of 29 degrees. And again, checking that your calculator is in degree mode, typing this in, gives you a quantity of about 27.4 units. Let's look at a couple more of these, and then we'll wrap up our notes. Notice the difference here. Now we're solving for x. Now, x is an angle measure. So from this angle, we have opposite and hypotenuse, so that's going to be sine. So we can say the sine of angle x equals opposite over hypotenuse. Now, if you're ever solving for an angle measure, we're not going to press just sine, cosine, or tangent on our calculator, because what we want to do is get rid of this sine. So we do the inverse sine of both sides. On the left, sine and inverse sine simplify, they're gone. If we type this quantity, inverse sine of 15 over 18, that'll tell us that our angle x is about equal to 56.4 degrees. And make sure you have a degree sign on there, otherwise it means 56.4 radians. Likewise, with this last example, from this angle x, we have opposite and adjacent, so we can say the tangent of x equals 14 over 17. Taking the inverse tangent of both sides gives us an angle measure of about 39.5 degrees. Okay, so I know I went through those last four examples relatively quickly, but really they're from your geometry or algebra days, so we should be okay with those. I have one final example. This one gives us a preview of our totally next chapter, chapter 5. Show that the following identity is true, and it goes back to, I'm going to flip back in notes until I get to this page right here. Look at these trig identities. We're going to use these identities to simplify one of these expressions given here. Now take a look at where it says cotangent of theta. One of those identities told us that the cotangent of theta equals cosine of theta over sine of theta. So I'm just going to rewrite this problem, but I'm doing one substitution. Everything else is going to be exactly the same. Now check it out. What's on the left here, we have sine of theta on top and sine of theta on bottom, so we can simplify this fraction. If we do that, we end up with the cosine of theta equals the cosine of theta. So by making that one substitution, we have shown that this identity is true. Basically what this is, it's a proof. I'm saying what's up here is true. We want to prove that it's true. And we can prove it's true by making a substitution, simplifying, and showing that, hey, what's on both sides of the equal sign is the same. All right, like I said, this is not something we're going to do a lot at this time, but we are going to see these quite a bit in the future. All right, that wraps up our notes for this unit. Take a look at this assignment on page 284. When you're done with that, you can move on to your next set of notes.